All right, welcome back. So last time we uh, examined this sequence, which uh, we found out the limit of the underlying terms goes to zero. So by the divergence test, it was inconclusive. And when we were writing this out, we came across this sequence right here: 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, and so on and so on. Okay, this sequence here is actually called the harmonic series. The harmonic series. And the simplest way to write it, we can get away from this complicated notation here and actually write this series as the sum as k goes from 1 to infinity of 1 over k, which is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, and so on forever. Now, this is referred to as the harmonic series because if you're familiar with music, and music with a stringed instrument in particular, um, if you pluck the full string, right, you get a tone. And then if you cut it and go and hold the string at half its length in the middle, pluck it, you'll get another tone. If you hold it at the 1/3, you'll get another tone. These were called harmonics. And so at each one of these things, you get the third tone, the quarter tone, and so on as you go through, touching on the string at different widths. And so they recognize those fractions as what are called harmonics. And so this series is a series that's adding up those things. And so hence it gets the name harmonic series. Now, our divergence test failed to hold, so it met the necessary condition for it to be able to converge. But is it sufficient? Does it close in quick enough? So the question we ask is, does this series converge? Does it converge? And so what I'm going to give you is a table that shows you the first few values of this sequence. So we're going to construct a little table here. Looking at the first few values, this actually comes from your textbook. So look at the sum based on n, and we're going to look at our partial sums, which would be the sum as k goes from 1 to n of 1 over k. So of course n equals 1, we would just be 1. N equals 2, be 1 plus 1/2 would be 3/2. N equals 3, it would be 3/2 plus 1/3, which would be 11/6. N equals 4, it would be that plus 1/4, will be 25/12. Okay, and then we're going to start getting bigger. So the textbook then gives you some of these larger values now. What if n is 10? What if n is 1,000? What if n is 1,000,000? What if n is this massive number? And what we find out is that 2.929, if n is equal to 10, 1,000, it comes out to be 7.49. When we put 1,000,000 in, it's 14.39. And when you put 10 to the 40th in, and of course I did not do this myself, this was some computer did this for the textbook, you get 92.68. In other words, this thing seems like it keeps growing. And now it's growing slower, but it's still continuing to grow. Okay, so it seems like this is probably going to diverge, right? Since it doesn't seem like this is settling into any particular number, it seems like it's going to diverge, okay? But we don't know that yet, right? We don't know for sure yet. So here's what we're going to do. Let's look at the graph of the 1 over x function. Let's look at the graph of the 1 over x function. Okay, so back here, let's look at the 1 over x function. Okay, so there it is, and we're only going to worry about the positive values. So we'll get over here to where I can just look at my positive values. I need to zoom up a little bit here. Okay. All right. So let's take a look at the graph here. Let's look at the graph here of this function. And we're going to use the graph. We're going to use the graph. And in the graph here, I'm going to start making some rectangles. I'm going to come in here and start making some rectangles. So I'm going to start here at x equals 1. At x equals 1, and I'm going to make the rectangle that comes up to its point in the graph, which would be 1, 1. So that's from 1 to 2. And then I'm going to start here at 2. And I'm going to go 1/2 to 3. And then at 3, I'm going to start on its point in the graph. Go from 3 to 4. And at 4, I'll start on its point in the graph. And go from 4 to 5. And then I'm going to start here at 5 on its point of the graph. Over to 6. And I'm just going to keep doing this. I'm going to keep doing this. Okay, I'm going to keep doing this. And then the other thing I want to talk about is the area beneath the graph. The area beneath the graph. The area beneath the graph. And we would continue this pattern on and on forever. So the first thing I want you to recognize is that when I'm taking and adding up my terms here, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 and so on, right? That's just the sum as k goes from 1 to infinity of 1 over k. Right? And you can see that in those rectangles. That's what the area of those rectangles is. Now, based on how I've set up the rectangles, every one of those rectangles is going to have an area that is slightly more than what's the area under the graph. So we can say with full confidence that this thing is greater than the improper integral from 1 to infinity of 1 over x dx. Okay. We know that the area of those rectangles has to be, because every one of them has area that you can't, that's above the graph. That's above the graph. So this thing here, whatever it is, has to be greater than the area beneath the graph. But we've actually seen the integral from 1 to infinity of 1 over x before. So let's recall, and if you don't remember it, it's okay, we're going to work it out. The integral from 1 to infinity of 1 over x dx. Remember, that's the limit as b goes to infinity of the integral from 1 to b of 1 over x dx. Right? That's the limit as b goes to infinity of ln, absolute value of x, evaluated between 1 and b. And that would be equal to the limit as b goes to infinity of ln of b minus the ln of 1. Ln of 1 is just 0, and as b goes to infinity, as we discussed previously, as b goes to infinity, ln of b also goes to infinity. Okay, so the area beneath the curve goes to infinity. So the integral diverges. The integral diverges. Okay? And so therefore, so the series of 1 over k also diverges. So it turns out the harmonic series diverges. It diverges because the integral diverges, and we can show that the harmonic series is greater than, right, is greater than the integral. Okay, so therefore, since the integral diverges, the harmonic series has to diverge as well. And so that's our big result there. This series, 1 plus 1/2 plus 1/3, and so on, actually grows without bound. Okay, it grows very slowly, but it grows without bound, and therefore it will go to infinity, and so therefore the series diverges.